am Dr. Surekarathi Samandi, Assistant Professor, Department of Aeronautical Engineering, Bharat Institute of Higher Education and Research. Yeah. So today let us discuss on the rudder design requirements. So yes, as we all know, the rudder is a control surface and it is located in the trailing edge of the vertical stabilizer. It is responsible for the aircraft's directional control. So in addition to that, it is mandatory for us to know some basic functions of the rudder. So let us discuss about the rudder requirements in this session. So there are 6 basic functions of the rudder, and we are here to discuss about the asymmetric thrust, which is the one engine in operative condition. Yeah. So look at this slide. The sketch illustrates the pedal and the yaw of the aircraft. So in the first figure, the pilot presses the left pedal and thereby the aircraft yaw towards the left side, left direction. So that hidden lines, no, so it indicates the action after the pressing of the pedal. So when you look into the second one, so here the pilot presses the right pedal and thereby tending the aircraft to take the right direction. So yaw towards right when the pilot presses the right pedal and yaw towards left when the pilot presses the left pedal. So the direction depends on the position of the pilot. So yes, so like there are 5 parameters to design a rudder. And the first one is the chord of the rudder, and the next one is the area of the rudder, and the third one is the span of the rudder, the fourth one the maximum rudder deflection, and the fifth one is the location of the inboard edge of the rudder. So location of the inboard edge of the rudder is this BRI. And you know that, right? So the chord of the rudder, you know, the span of the rudder, BR indicates the span of the rudder, the area of the rudder, and the maximum deflection of the rudder. So the rudder will not be allowed to deflect to the maximum extent. During designing itself, they will design to a certain extent. It may be like a plus or minus 30 degree or plus or minus 25 degrees. So that deflection is actually set during the designing itself. But the designer have to ensure that that maximum deflection of the rudder is sufficient to operate during the some unfavorable conditions. So the set of the maximum deflection of the rudder plays a critical role. And the rudder is connected to the vertical tail with the help of the hinges. So next one is the directional control via rudder deflection. In the previous slide, we have seen about the pedal control. So when the pilot presses the left pedal, the aircraft will yaw towards the left. When the pilot presses the right pedal, the aircraft will yaw towards the right. So how about the rudder deflection? Yes. So this is the top view of the aircraft, and delta R is the deflection of the rudder. R indicates the rudder, and LV is the side force, and V is the combination of the vertical stabilizer and the vertical tail and the rudder combination, and NA is the yawing moment of the aircraft. CG, of course, we know, and LV is the momentum, and V is the free stream velocity. Yes. So now let us consider that the pilot deflects the rudder to an angle of delta R. The moment the pilot is deflected, what happens to the air molecules ahead of the rudder? It will get compressed. So when it gets compressed, what happens? The pressure force will be generated in the direction like towards that deflection of the rudder. So it will be in the opposite direction to the deflection of the rudder. So that side force is nothing but LV. So due to the deflection of the rudder, the side force is created, and which in turn creates the yawing moment in that particular direction. So since it is in the towards the right direction. So as far as this diagram is concerned, the rudder is deflected towards the left side, so thereby creating a side force in the right direction, so which in turn creates the yawing moment in the counterclockwise direction. So this is how the rudder deflects. So now when the rudder is deflected towards the right, what happens to the yaw direction? It is also towards the right. So when the rudder is deflected towards the left direction, the aircraft will yaw towards the left. So now correlate the pedal movement, the rudder deflection, and the direction of the aircraft. So when the pilot presses the left pedal, then the aircraft, like the rudder, will deflect towards the left, thereby creating the yaw towards the left. When the pilot presses the right pedal, the rudder will be deflected towards the right direction and thereby tending the aircraft to yaw towards the right. So just keep that in mind. And so these are all the aerodynamical characteristics which are related with the rudder deflection. And the first one is side force. So like because of the deflection of the rudder, the side force is generated, LV. So what is the side force? So as we already know, it is a coefficient of the side force into the dynamic pressure into area of the vertical stabilizer. So side force is represented by LV, and it is Q bar. Q bar is the dynamic pressure of the vertical stabilizer. SV is the area of the vertical stabilizer, and CLV is the coefficient of the side force. Yes. So the next one is the coefficient of. So how am I going to calculate the coefficient of the lift coefficient of the vertical tail? So CLV. CLV is the function of the vertical tail airfoil section. So VA, right? So it is nothing but the vertical tail airfoil section. And beta, we know that beta is the side slip angle. So the coefficient of the vertical tail, the coefficient of the vertical tail depends on the side slip angle beta. So it also depends on the rudder deflection delta R. So the yawing moment coefficient is linearly modeled as CLV is equal to CLVA plus CLV beta into beta. So CLV beta is dou CLV by dou beta. The change in the coefficient of the vertical tail to the change in the slip angle, side slip angle, plus CLV delta R, so which is nothing but dou CLV divided by dou delta R. Yes. So the next one is the aerodynamic yawing moment, NA yawing moment. In the previous diagram we have seen, right? So that NA yawing moment, it is the function of the dynamic pressure, wing area, wingspan, and the coefficient of the yawing moment. So as we know, the moment is the force into perpendicular distance, force into that moment arm. So here the moment arm is the wingspan. So the yawing moment is formulated as Q bar S into Cn into B. So Cn is the yawing moment coefficient. And of course, it's similar to the vertical tail lift coefficient. The yawing moment coefficient is also a function of the aircraft configuration CNO and the side slip angle beta, rudder deflection delta R. So in addition to that, it also depends on the aileron deflection. So as we know, like both the aileron and the rudder are the coupled control surfaces. So both depends on each other. When the rudder is deflected, definitely there is the possibility of roll in the aircraft. Similarly, when the aileron is deflected, the aircraft will undergo yaw. So both are coupled, and that is the reason why we have included the aileron deflection in the yawing moment coefficient. And the yawing moment coefficient is linearly modeled as Cn is equal to Cn8 plus Cn beta into beta plus Cn delta A into delta A plus Cn del R into del R. Yes. So C and delta R. So it is referred as the aircraft yawing moment coefficient due to the rudder deflection derivative. And hence it is also called as the rudder yaw control power. So we can also term that as rudder yaw control effectiveness. Okay. So what is C and delta R? C and delta R is the aircraft yawing moment coefficient due to the rudder deflection derivative. So you can call that as rudder yaw control power. It can be also termed as rudder yaw control effectiveness. And it is actually measured by the rate of change of yawing moment with respect to the rudder deflection angle. Yes, so in the non-dimensional form, you can represent C and delta R as dou Cn by dou delta R. Okay, so C and delta R is dou Cn by dou delta R. So it is represented in terms of non-dimensional form. Yes. So in addition to the rudder yaw control power, rudder yaw control effectiveness, you can also term that as directional control derivative. So dou Cn by dou delta R can also be represented as the directional control derivative. And it depends strongly on the vertical tail size. That is the tail size of the vertical stabilizer, the vertical tail moment arm, and it is determined by minus CLAV. So CLAV is the vertical tail lift curve slope. P bar V is the vertical tail volume coefficient. So how do you represent vertical tail volume coefficient? It is defined as the ratio of the LV into SV by B into S. So LV is the momentum, SV is the area of the vertical stabilizer to the B, span of the wing into the area of the wing. Okay, so the vertical tail volume coefficient is defined as LV SV by B into S. And eta V. So eta V is the vertical tail dynamic pressure ratio. So it is the ratio of the dynamic pressure of the vertical tail to the dynamic pressure of the free stream. So it is QV by Q infinity. And tau R. So tau R is referred as the rudder angle of attack effectiveness parameter. So what is tau R? So tau R is the rudder angle of attack effectiveness parameter, and it is the function of the rudder chord to the vertical tail chord ratio. Okay, so it is the function of CR by CV. It is the ratio of the rudder chord to the chord of the vertical tail. Okay, so remember it. And BR, of course, BR is the span of the rudder, and BV is the span of the vertical tail. So the directional control derivative, it depends on all these parameters. So it depends on the size of the vertical tail. It depends on the span of the vertical tail. It depends on the area of the vertical tail. Chord of the vertical tail. So it depends on the size of the vertical tail and the vertical tail moment arm. Okay, so don't forget it. So this is what C and delta are. And so now let us get into the rudder design requirement. So when you deal with rudder design requirement, it is like while designing, it is not like the rudder is designed for a particular function for all phases of aircraft. It's not so. The design of the rudder, it depends on the aircraft. So what they are designing, the rudder plays a different role for different phase of the flight in various aircrafts. So there are 6 major functions. So the first one is the directional control for balancing asymmetric thrust. So asymmetric thrust is one engine inoperative condition. So like only in case of a multi-engine aircraft, this problem comes into picture. So if it is a single engine aircraft, then there is no point in asymmetric thrust at all. So thrust will be generated from one engine. So asymmetric thrust is there is no any symmetric in the thrust generation. So it may be a twin engine aircraft or a 4-engine aircraft, 6-engine aircraft. So, so this comes into picture only in case of a multi-engine aircraft. And the next one is the crosswind landing. So you see, like, so crosswind landing happens in all aircraft. So during landing, because of the influence of the crosswind, there may be possibility of the aircraft to move away from the runway. So rudder should function in such a way that the aircraft must maintain the alignment with the runway during the crosswind landing. So like crosswind landing, it can be experienced in all kinds of aircrafts. The next one is spin recovery. So spin recovery, when the you see when the pilot operates both yawing and stall at the same moment, then there is the possibility of the spinning or the auto rotation. So the aircraft must be able to oppose the spin rotation, and it should recover from the spin. So this mainly occur only in a spinnable aircraft. It is not it's not experienced in all type of aircrafts. So only in spinnable aircrafts. So this spin and recovery plays a vital role. And the next one is the coordinated turn. So like the aircraft must be able to coordinate a turn. So the turning is a maneuver which is experienced by all kinds of aircraft. So the aircraft must be able to coordinate a turn. And the next one is the adverse yaw. So as we know that the aileron and the rudder or the coupled control surfaces, when the aircraft undergoes rolling, there is the possibility of the aircraft to yaw also. So similarly, when the aircraft undergoes yawing motion, when it yaws, there is the possibility of the rolling in the aircraft. So that is nothing but the adverse yaw. So the rudder must be able to overcome the adverse yaw that is produced by the aileron. So of course, this is also experienced in all kinds of aircrafts. And the last one is the glider slope adjustment. So this is experienced only in the glider aircraft. So the glider slope adjustment for a glider, the aircraft must be able to adjust the glide slope by increasing the aircraft drag. So it should increase the aircraft drag using the rudder deflection. So these are all the 6 functions of a rudder. So rudder plays different roles for different phases of the flight in various aircrafts. Yes, so so today let us discuss about the asymmetric thrust, which is one engine in operative condition. So this is Boeing 777, and as you see, the right engine is actually, it is a failure engine. You can see the fire in the right engine. So which means that there is no any thrust produced in this engine. So the thrust is only experienced in the left engine. So what does it mean? So thrust is produced in the left engine, whereas the thrust produced in the right engine is 0. So the thrust is not symmetric, and that is the reason why we call this as asymmetric thrust. So when that engine is not working, what happens? There is a possibility of the aircraft to yaw towards the failure engine. So that is overcome by the rudder deflection. So that is what we are going to see. So like before getting into the asymmetric thrust condition, let us just consider the aircraft, and that aircraft yaw due to the side slip, due to some disturbance, the aircraft yaw due to that disturbance. So now look at this figure. the relative airflow, right? The arrow mark. So that is the equilibrium and the steady flight path. And due to the side slip, the aircraft deviated from that path and to the side slip angle of beta. So now the aircraft is moving in the dotted lines, hidden lines. But actually speaking, that is not the flight path, right? It should move along the relative flow direction, airflow direction. So now, what should happen? So the aircraft should undergo some rudder deflection, and it should tend to come back to its original position. So now the rudder is going to play a role. So you see the rudder. So the rudder should be deflected. So the rudder depends on the direction of the yaw. So now the aircraft should yaw towards its right. So which means that the rudder should be deflected towards the right direction. So when it deflects towards the right direction, there will be a side force generated towards the left. That side force creates a yawing moment in the counterclockwise direction. That is N plus N, yawing moment. So which in turn, if at all, if it is directionally stable aircraft, then the aircraft will come back to its original position. That is, it will move in the flight path direction. So got it? I'll just repeat it once again. Yeah, the relative airflow is the direction of the aircraft. It is the flight path direction. And due to some disturbance, the aircraft is deviated from its path to an angle of beta. So that beta is nothing but the side slip angle. Now, so it is deviated from its path. The aircraft should come back to its original position, like it should move in its original flight path. So now that is that means that the aircraft should yaw towards the right. So when the aircraft should yaw towards the right, it means that the rudder should be deflected towards the right. When the rudder deflects towards the right, what happens to the side force? The side force will be generated in the left direction. So thereby creating a yawing moment in the clockwise direction. So this yawing movement tends the aircraft to come back to its original position. Okay, so this is yaw due to the side slip. And now one engine in operative condition. So you see, so as far as this diagram is concerned, that the left engine is a failure one. So the right engine is working, and that's the reason why it is producing some thrust. So because of this asymmetric thrust, there is the possibility of the thrust yawing moment, and that moment will be towards the failure engine. So the aircraft will tend to move towards the change the direction towards the failure engine. So which means that it will be deviated from the original flight path. Equilibrium condition. So what the rudder should do? So the rudder should make the aircraft to come back to its original position. So the rudder will be deflected towards the live engine direction. So thereby creating a side force towards the failure engine. So when the side force is created towards the failure engine, so the rudder yawing moment will be created in the clockwise direction. So now look at this diagram. The thrust yawing moment is in the anti-clockwise direction. The rudder yawing moment in the clockwise direction. So these moments will be nullified and finally tending the aircraft to move in its original path, flight path. So got it? So this diagram also illustrates the side slip. So the side slip angle is somewhere, and because of the side slip angle, the rudder is deflected, and the side slip yawing moment is generated. So this side slip and this thrust yawing moment is actually different. So this side slip yawing moment is due to the side slip of the aircraft. The thrust yawing moment is due to the asymmetric thrust. So just don't mix both. Try to differentiate both the cases. Okay. So yeah. So there may be some problems expected. So just a large transport aircraft with the maximum takeoff mass of 65,000 kg is equipped with two turbofan engines, each generating 116 kilonewton of thrust. The lateral distance between the two engines is 12 meters. And the maximum allowable rudder deflection is plus or minus 30 degrees. So it is set during the design of the aircraft. So other characteristics of the aircraft are as follows. They have given other parameters. So the question is the rudder acceptable for maintaining the directional trim in an asymmetric thrust flight condition? It's a multi-engine aircraft. There are two engines, and the distance between the two engines is 12 mm apart, and each creating 116 kilonewton of thrust. And they've asked if an engine failure during the flight condition, so is it is possible for the rudder to tend the aircraft to come back to its original position, to maintain its equilibrium conditions. That is what is the question is. So what you have to do, you have to calculate the deflection of the rudder. And if the value of the rudder deflection is less than the maximum allowable rudder deflection, which is mentioned in the question, it is mentioned as plus or minus 30 degrees. If the obtained value of delta R is less than plus or minus 30 degrees, then for sure it is capable, this is acceptable. The rudder is capable of maintaining the directional trim. So you have to use this directional control derivative C and delta R, calculate it, and from that you just calculate the value of deflection of the rudder and check the value of the deflection of the rudder. If that value is less than the maximum allowable rudder deflection, then the rudder is acceptable. So the rudder acceptable for maintaining the directional trim, no issues at all. But if this value is greater than plus or minus 30 degrees, then it is not possible by the aircraft to maintain its equilibrium position. So got it? So whenever you solve a problem, try to understand the concept behind that issue. If you understood the concept, then it is easy for you guys to tackle that problem. So got it? So that is all about the asymmetric thrust or the one engine inoperative condition. So let us discuss about the other functions of the rudder in our next session, next video. Okay. Thank you guys. Thank you.